let's go ahead and get started. Let me just start with a couple administrative comments, if I can remember them. The first comment is that there is a makeup class tomorrow. At 4 p.m. In the piano room, which is on the second floor. I forget the number. I think it might be 211. And there's also a makeup class next Thursday as well. Second announcement, in their infinite wisdom, the McGill bureaucrats have rescheduled the final exam due date for April 13th. It used to be April 15th. So that means, I think, a Wednesday instead of a Friday. We'll see what we can do about that. Yes,
yeah,
comment.
That part of those 24 hours would then overlap with my quantum mechanics exam.
You're in quantum too?
Yeah.
Yeah. That's because you're a U2.
Yes.
And that's because you don't matter. Because this is a U3 class, right? So they go according to what conflicts will happen for U3 people. And then there's some other exam that people take at 2 p.m. on the 13th. I don't know. Whatever. We'll just wait till they make up all their minds about when exams are going to be, and then we'll work with that. So we'll put a question mark here. And I had a third announcement, but I can't remember what it was. Oh, yeah. I handed out a problem set last week, which is due Tuesday. That's the announcement. Okay. Okay, let's get started. So today, what I would like to do is finish our discussion of differential geometry and the mathematics of curved spaces. And then, by the end of class today, we'll dive into the discussion of how we formulate physics in curved spaces, leading up to our discussion of Einstein's equations and the formulation of general relativity, which will probably happen next class and then proceed for the rest of next week. So today is really going to be the last hurrah of the mathematical portion of this course, where we complete our discussion of differential geometry, curvature, and so forth, before diving into real physics, which will occupy us for the rest of this class. So let me just remind you of where we left off last time. So we were trying to make precise the notion that a geometry is curved, and we wanted to discover some sort of covariant or tensorial formulation of the notion that space-time is curved. So roughly speaking, the idea is that space-time is curved at a point if, when you transport a vector around a very small loop at that point, so if you have a very small loop around a point, then you can ask the question of whether the vector, when transported around that loop, will come back to itself. If the answer is yes, then the spacetime is flat. If the answer is no, the spacetime is curved. And we realized that the failure of a vector to come back to itself for very small loops is the same as the failure of covariant derivatives to commute with one another. And so we defined an object called the Riemann Curvature tensor. How is this object defined? Well, the Riemann Curvature tensor is a 1, 3 tensor, which is defined by the formula R rho sigma mu nu P sigma is the commutator of two covariant derivatives acting on V. So the Riemann curvature measures the failure of covariant derivatives to commute with one another when acting on a vector. Now, one could also ask about what the quantity is that measures the failure of derivatives to commute with one another when acting on a tensor or a one form or something like that. And it's a straightforward, although occasionally tedious exercise to show that that also is given by something that's determined in terms of the Riemann curvature tensor. So that's something that you could work out if you were so inclined. So for example, I believe it might be worked out in the text, or you could work it out for yourselves, what the tensor is that measures the failure of covariant derivatives to commute with one another when acting on one-forms. That, it turns out, to be a slightly different structure, which is built out of the Riemann Curvature tensor. So the Riemann Curvature is the tensor that packages the idea that vectors transported around little loops don't come back to one another. And we derived last time an explicit formula for the Riemann Curvature tensor in terms of the Christoffel symbols. So the Christoffel symbols, I remind you, are the objects with one upper and two lower index, which are used to formulate both the geodesic equation as well as the covariant derivative. So the Christoffel symbol is the correction term that arises in the covariant derivative. It's built out of the metric, so let me remind you of the formula. So the Christoffel symbol involves first derivatives of the metric, and it's essentially the correction term that you have to add to the covariant derivative, to the partial derivative, in order to make it covariant and make everything transform in a nice tensorial way under coordinate transformations. The Christoffel symbol itself is not a tensor, but one can take a certain combination of derivatives of the Christoffel symbol plus the Christoffel symbol squared and get a tensor, and that tensor is the Riemann Curvature tensor. So the Riemann Curvature is this quantity which is built out of second derivatives of the metric, which is a measure of the failure of the covariant derivatives to commute with one another. And I've given you some complicated but completely specific formulas for the Riemann curvature. So there are a lot of indices flying around. It's a little early in the morning for so many indices. But once you get used to manipulating these objects, they won't seem nearly so opaque as they do right now, probably. So what do we know about the Riemann curvature tensor? Well, space-time is flat if the Riemann curvature tensor vanishes. And in that case, there's a coordinate system where the metric is equal to a constant. And what we began doing at the end of last class was trying to understand a bit more about this notion of curvature by choosing what are known as Riemann normal coordinates. So the idea of Riemann normal coordinates is motivated by the Einstein equivalence principle. So remember, the Einstein equivalence principle tells us that at any point, say x naught mu, in space-time, there is a coordinate system say x mu hat, such that at the point x naught, the metric written in these coordinates is just the flat Minkowski metric. And moreover, we saw last time that one can even, by carefully choosing this coordinate system, set all of the derivatives of the metric to be equal to 0 at the point x naught mu. So what does this mean physically? This means that you're choosing a coordinate system such that at this point x naught, the Christoffel symbol vanishes. Right? Because the Christoffel symbol is built out of first derivatives of the metric. So what does that mean? That means there are no fictitious forces. So you're choosing a freely falling coordinate system at this point. So for example, if you're in an elevator, or let's say if I were describing the physics of gravity in a small neighborhood of this room, then I could approximately describe the gravitational force as a constant. And then I could choose an accelerating coordinate system where Newton's laws appear to hold. I could just define a coordinate system that is freely falling, namely accelerating down with acceleration equal to 9.8 meters per second squared. And then in that coordinate system, there would be, Newton's laws would look just like they look if there was no gravity. So that would be a simple example of Riemann normal coordinates. But what we argued yesterday is that one can always choose Riemann normal coordinates around any point in any space-time. And in those coordinates, the first derivative of the metric vanishes, but the second derivative does not. And so that means that even though the Christoffel symbol vanishes, the Riemann tensor, which tells you about the curvature of space-time at that point, does not. So the way that you should think about the Riemann curvature then is that in these coordinates, the metric is given by the flat metric plus terms that are order x hat squared. And how many degrees of freedom does it take to describe those terms that are order x squared, these quadratic deviations from being exactly flat at this point? Well, we did a little counting last time, and we saw that there are 100 possible second derivatives of the metric in 4 dimension, and only 80 possible coordinate transformations at that order, meaning that there are physically 20 degrees of freedom in these second derivatives of the metric. And what we will see is that the Riemann tensor is nothing more, nothing less than a coordinate invariant way, that is to say, a covariant or tensorial way of packaging all of the information in the second derivatives of the metric. So you should think of the Riemann tensor also as a way of packaging together all of the information in the second derivatives of the metric. So that is something that I am going to discuss right now. And in particular, what I'm going to do is work out the Riemann curvature in these Riemann normal coordinates. We'll see that it has a very simple form, which will allow us to determine all sorts of nice properties of the Riemann tensor, count its number of degrees of freedom, and then we'll move on from there. But before I do so, let me pause and see if there are any questions. I appreciate the fact that this is a fairly sizable amount of material that is all probably quite new to you. So pay careful attention to your problem sets where you'll develop a lot of intuition for dealing with these objects. I think that general relativity and differential geometry is one of those subjects where you could listen to lectures all day long, but until you start trying to do calculations, you won't really develop a sort of physical intuition and a feel for the subject. Okay, so let's go ahead and ask what the Riemann tensor looks like in these Riemann normal coordinates. And in particular, what I would like to compute is not the Riemann tensor with all of its indices raised, but rather the Riemann tensor as I defined it had one upper index and 3 lower indices. So what I would like to do is study the object with 4 lower indices, where I just lower one of the indices with the metric as usual. So what does this guy look like in Riemann normal coordinates? So this stands for Riemann normal coordinates, not Republican National Committee. So in Riemann normal coordinates, what does this guy look like? Well, this is G rho alpha times, let me scroll up here, this complicated expression here involving the derivatives of the Christoffel symbol and the Christoffel symbol squared. Well, in Riemann normal coordinates, if I'm just looking at the point x0, the Christoffel symbols vanish, although their first derivatives do not. So that means that I can ignore all of these terms here involving the square of the Christoffel symbol. And I have these terms involving the derivatives of the Christoffel symbol. And those are the only guys that will contribute to the Riemann tensor in Riemann normal coordinates. Of course, there are, in addition to this term, plus terms that are of order x hat. So here we are evaluating the Riemann tensor at the point x naught, where the first derivative of the metric vanishes. It's important to realize that although the first derivative of the metric vanishes, and so the Christoffel symbols vanish at the point x naught, their derivatives do not. So the second derivative of the metric and the first derivative of the Christoffel symbol do not vanish. If they did, the Riemann curvature would be equal to 0, space-time would be flat, and the metric could just be set equal to a constant everywhere by a judicious choice of coordinates. Is that clear? I see one or two confused-looking faces. Any questions? Okay, good. So let's work this out a little more explicitly. So I remind you that the Christoffel symbol is 1/2 times the inverse metric. Oh, by the way, I was writing hatted coordinates up above for the Riemann normal coordinates. I've dropped the hats here because I'll never get anywhere if I have to write hats over all of my indices. But if you like, you could insert hats over all of these indices. So what is this guy? This is this particular combination of the inverse metric, oops, Jesus Christ, and its first derivatives. Okay. Now, let's imagine plugging this expression into this formula here, where I'm computing the Riemann curvature. So the first thing that you should notice is that if the derivative were to hit this guy, then you would just have something involving derivatives of the inverse metric times derivatives of the metric, which would vanish at the point x naught mu. So it would vanish up to terms of order x hat that we're neglecting because we're only evaluating the Riemann tensor at the point where x is equal to 0. So I only need to look at the terms where the derivative hits this guy. And moreover, at the point x hat 0, g is just given by eta mu nu. And so I will now proceed to raise and lower indices using eta mu nu, neglecting terms that vanish at higher order, that vanish at order x hat to the 0. So I can just replace, so this g here is going to be given by eta rho alpha, plus terms that are of order, higher order in x hat. And so if I'm only working on order x to the 0, I can just lower and raise all of my indices using eta mu nu, using the flat Minkowski metric, which is what I'll do when I write out my expression here. So what do I have? So I have 1/2 times the derivative with respect to mu of, well, let's work this all out. So I have, an eta rho alpha times this guy here, an eta alpha beta with two upper indices, which turns into a delta beta rho. So that means that in this expression that I'm going to write, all of the betas here in the Christoffel symbol will become rhos. So I have the derivative with respect to nu of g sigma rho plus the derivative with respect to sigma of g nu rho minus the derivative with respect to rho of g sigma nu. And then we subtract off the exact same thing over here with mu and nu switched. So d nu of d mu g sigma rho plus d sigma g mu rho minus d rho g sigma mu. Okay, now let's simplify this a little bit. So if I've done everything correctly, there should be a cancellation here. So we notice that this term will cancel this term, right? That's just the equality of mixed partial derivatives. And what we're left with is a sum of 4 terms involving second derivatives of the metric. So we have d mu, d sigma, g mu rho, minus d mu, d rho, g sigma nu, minus d mu, d sigma, g mu rho, minus plus d nu, d rho, g mu sigma, plus terms that will vanish at the point x equals 0. And this is the formula for the Riemann tensor with all lower indices in Riemann normal coordinates at the point where we're setting the derivative of the metric equal to 0. So this is the particular combination of second derivatives of the metric that give us the Riemann tensor in this coordinate system. So, are there any questions before I continue? Yes. Rho is one of the indices of the Riemann tensor. So rho is a free index on both sides of this equation. I guess, no. So here it is on the left side and on the right side. And then this is my expression for gamma. Here it is on the left side, on the right side, so on and so forth. Is that, okay. Okay. Any other questions? Okay. So let's stare at this expression for the Riemann tensor for a few minutes. So the first thing that is obvious from this expression is that the Riemann tensor has a lot of symmetries. Okay. What sort of symmetries does the Riemann tensor have? Well, remember, as I pointed out to you last class, the Riemann tensor is going to be antisymmetric in mu and nu. That's because it involves the commutator of a derivative with respect to mu and a derivative with respect to nu. So by construction, it's going to be antisymmetric in mu and nu. So let's check that. So what happens if we switched the indices mu and nu? Well, if we switched the indices mu and nu, this first term here would get exchanged with that third term, and this second term would get exchanged with the fourth term. And indeed, those terms differ by a relative minus sign. So you can see explicitly in this expression that, as expected, the Riemann tensor is going to be antisymmetric in the second pair of indices. Yes. Oh, I'm sorry. Thank you. Yes. So if you switch the last two indices, then the Riemann tensor will pick up a minus sign. That's not a surprise. But you can see here that this particular combination of second derivatives of the metric has a lot of other symmetries in addition to this interchange of the last two indices. For example, we could ask what would happen if you interchanged the first two indices. Well, if you interchange the first two indices, rho and sigma, then this first term here will be interchanged with this second term. And likewise, the third term will be interchanged with the fourth term. Those terms differ by a relative minus sign, So when you switch the first two indices, you also pick up a minus sign. So the Riemann tensor is also antisymmetric in the first pair of indices. So you can now guess what the next symmetry is going to be. There should be another symmetry where the first term is interchanged with the fourth term and the second term with the third term. And if you stare at it for a second, you'll see that that will happen if you interchange the first pair of indices with the second pair of indices. So if you replace rho by mu, if you switch rho with mu and sigma with nu, what happens, that first term right here will get interchanged with the fourth term and the second term with the third term. Here, there's no relative minus sign, so that just means that the Riemann tensor is symmetric when we interchange the first pair of indices with the second pair. So those are all of the obvious symmetries. In fact, it turns out there's one more symmetry which is less obvious in these coordinates, which is the fact that if you anti-symmetrized all of the indices, you would get 0. So that's easy enough. It's not exactly obvious from what we have written here, but it's easy enough to prove. When you anti-symmetrize the indices, you just have to add up a bunch of terms. What is it? It's 24 different terms, right? Because there are 24 different permutations of 4 elements. So you take the Riemann tensor, which is the sum of 4 terms, and then you add the 24 permutations of that, and so you have, 96 different terms that you add together. You start canceling, and then you finish canceling, and you get 0. So I won't bother going through that here. It's perfectly straightforward to prove. In fact, I might assign you to do it on a problem set. I don't actually remember. That'll be exciting. So these, then, are all of the various symmetries of the Riemann tensor under the permutation of indices. In fact, sometimes this final one is written in a slightly different form. So you can actually check that using the first 3 symmetries that I have written up above, we can write this first symmetry not as an anti-symmetrization on all its indices, but instead just an anti-symmetrization on any 3 of its indices. Okay, that makes your life easier. That divides by 4 the number of terms you have to add together in order to check this. It's still a hell of a lot of terms, so I'm not going to bother going through it here. 24 different terms now that you would have to add together. But it's perfectly straightforward to check. Just by manipulation, just by straightforward cancellation of the various terms in this expression. Okay. So the Riemann tensor is not just any 4-index object. Because of the way the Riemann tensor is constructed, it has a lot of different symmetry properties. And so the question that I would then like to ask is, how many degrees of freedom are there in the Riemann tensor? This is, I think, an instructive little exercise, which will hopefully convince you that the Riemann tensor contains all of the possible information contained in the second derivative of the metric. So let's ask then, how many degrees of freedom will there be in the Riemann tensor, given the fact that it obeys all of these various boxed identities that I have written up above? Well, let me just stare at these equations for a second. So the Riemann tensor is a 4-index object. And a priori, it's sort of difficult in your mind to imagine counting the number of degrees of freedom in a 4-index object. You're very used to counting the number of degrees of freedom in 2-index objects like matrices. you know how to count the number of degrees of freedom in a symmetric or an anti-symmetric matrix. And happily, what this third identity is telling you is that you can actually treat the Riemann tensor, if you like, as a matrix, where the first pair of indices describe one row of the matrix, and the second pair describes a column of the matrix. And so you should think, you could, if you wanted to, think of the Riemann tensor as a symmetric matrix, where the symmetry that I'm discussing is the symmetry of the interchange of the first pair of indices and the second pair of indices. And how many degrees of freedom are described by the first pair of indices? Well, each individual pair of indices looks like an anti-symmetric D by D matrix. Right? That's what the first two identities are telling you. So each pair of indices is like an anti-symmetric D by D matrix, which has, let's see, D times D minus 1 over 2 degrees of freedom. That's just the number of independent entries of a D by D matrix. So the first pair of indices can take one of D minus D over 2 values, and the second pair of indices can take 1 over D minus D over 2 possible values. So the whole Riemann tensor is described by the two together which are like a symmetric matrix of dimension D minus D over 2, D times D minus 1 over 2, which will have, let's see, a symmetric matrix of dimension n has n times n plus 1 over 2 degrees of freedom. So it'll be D times D minus 1 over 2 times D minus 1 over 2 plus 1 all over 2. So it'll have that number of degrees of freedom. So there then we have counted the number of degrees of freedom in a 4-index object obeying these first three equations. And now we just need to take into account this fourth equation. So how many constraints does this fourth equation impose? Well, it imposes D choose 4 constraints, which is the number of possible degrees of freedom in an anti-symmetric 4-index object. So that's D factorial over 4 factorial times D minus 4 factorial. So the total number of degrees of freedom is, let's see, it's 1/2 times D minus 1 over 2 times D minus 1 over 2 plus 1 minus D choose 4, which is D factorial over 4 factorial times, well, let me just write that out explicitly. That's D times D minus 1 times D minus 2 times D minus 3 over 4 factorial, which is 24. So this is D choose 4. And so you can then it's just a simple calculation to check that this can be simplified. And it's 1/12 D squared times D squared minus 1. So this is the number of degrees of freedom of the Riemann tensor in D dimensions. Any questions on that? This was just a quick sort of counting of the number of degrees of freedom based on the manipulation of indices. Are there any questions on the logic of that calculation? So the number of degrees of freedom in the Riemann tensor is 1/12 D squared times D squared minus 1 in D dimensions. So, for example, in the case that we will almost exclusively be talking about this semester, in 4 dimensions, the Riemann tensor has, let's see, 1/12 times 4 squared times 5 squared, times 3 squared degrees of freedom, which, there's a plus, let's see. Yeah, there's a +1, isn't there? There better be a +1 there. Yep.
Minus is you went d minus 1 squared instead of d squared minus 1.
Oh, I'm sorry. Thank you. Good. Excellent. Okay. Otherwise, we would have to reevaluate the course curriculum. But indeed, if we work this all out, we find that the Riemann tensor in 4 dimensions has 20 degrees of freedom, which we argued last class was the number of degrees of freedom in the second derivatives of the metric which cannot be removed by changes of coordinates. So the second derivative of the metric, as you remember, had 100 degrees of freedom, but there were 80 possible coordinate transformations that one could do at that order, leaving you with 20 degrees of freedom. And what we see now is that the Riemann tensor contains all of the information in those 20 degrees of freedom. So the Riemann tensor contains all of the information in the second derivatives of the metric. That's good news. Why is it good news? In physics, all of our equations of motion are second order. If the metric is your dynamical variable of general relativity, then your equations of motion, first of all, must be tensor equations because they should be independent of your coordinate system. And second of all, they should involve second derivatives of the metric. And we have seen now that the Riemann tensor is the unique object that we can construct which contains all of this information. That means the equations of motion of general relativity need to be an equation for the Riemann tensor. And in the next few lectures, we will explore in more detail how we should formulate a theory of gravity and decide exactly what the correct equation of motion should be. Question?
How is it that the Riemann tensor and the equations of motion have the same degrees of freedom? That's something fundamental.
Right. So, for example, last time when I counted the number of degrees of freedom in the second derivatives of the metric, and I subtracted off the number of degrees of freedom in the change of coordinates, I only did that in 4 dimensions because I'm lazy and, that's all I felt like doing. You could go through the exact same argument in any number of dimensions, and you would get the answer that I wrote down for the number of degrees of freedom in the Riemann tensor. So, yeah, I don't know if that answers your question, however.
How is it that the Riemann tensor exactly...
let's see. How is it? I guess I don't quite know how to answer that question. The Riemann tensor, let's put it this way. We could start with the following. We could start just by writing down the second derivative of the metric. So there's 100, that's a 4-index object with 100 degrees of freedom. And then you could ask then of course the second derivative of the metric doesn't transform as a tensor under coordinate transformations. So it doesn't have any coordinate independent meaning. But then you could start asking what things you could add to it which would make it into a tensor. And my claim is that if you start it, this would be a purely constructive way of building up the Riemann tensor. And what I claim is that if you started doing that, you would discover that the only thing that you could build, which involves only the metric, its first derivative, and its second derivative, which transforms as a tensor, is the Riemann tensor. That's a true statement. I could have, if I wanted to, derived the subject in this way. But I chose instead to motivate it a little bit more physically, involving little loop, transporting vectors around loops. But I could have derived it that way. It might have been a very difficult derivation. I wouldn't envy the person who derived it that way. But it's a true statement. Yes.
When we sort of investigate the symmetricity indices for Riemann tensor, we use Riemann normal coordinates, and we just look at the sort of remaining part. How do we know that the elements that
yes. Okay. That's an excellent question. Let me paraphrase your question a little bit. That's actually a very good thing that I forgot to mention. So, what we have shown, actually, using this expression here for the Riemann tensor in this particular coordinate system, is that what is true is that at the point x equals 0, this identity is true. But, so, for any point in space-time, there is a coordinate system where at that point, these two tensors, the guy on the left-hand side here and the guy on the right-hand side, are equal. Okay. Now remember the magic of tensors. What is the magic of tensors? The magic of tensors is that if you have an equation which is true in one coordinate system, it is true in all coordinate systems. Okay? So that means that take your favorite point in space-time, find a coordinate system where where the first derivatives of the metric vanish, then this identity will be true at that point. And what you've then shown is that it'll be true at that point in every coordinate system. And in particular, it'll also be true at every point, because I didn't specify that I had to work at one point or another when I did this. So at any given, it's a slightly subtle argument, and it involves the magic of tensors, right? If we tried to do this, this is why we need to use things which transform in a nice way under coordinate transformations. Because I'm using, in writing this down, the fact, these equations are true not just in Riemann normal coordinates, but they're always true, even in coordinates where the first derivatives of the metric don't vanish. The reason being that if you can show that an equation is true in one coordinate system, and the only things that appear in this equation are tensors, then that equation is true in every coordinate system. That's a good question. I meant to say that, but I didn't mention it. Yes. Good. Yes. Yes. Yeah. I understand the philosophy. The philosophy of your question is a good one. So the question was whether these symmetries lead to conserved quantities. The symmetries which lead to conserved quantities are continuous symmetries. These are discrete symmetries. Right, they're just interchange symmetries. So, moreover, we'll see, probably not next week, maybe next week, but certainly if not next week, the following week, exactly how Noether's theorem does work in general relativity. Remember that a symmetry in the context of Noether's theorem is a change of variables which leaves the equations of motion invariant. We will see precisely how to think about that in the language of general relativity. So I would defer any discussion of Noether's theorem until then, but that's a good direction to start thinking in. Yes. Other questions? Good questions. Everyone. Okay. So, let me now just mention one final identity, which is obeyed by the Riemann tensor. So I've shown you up above all of the various identities which are obeyed by the Riemann tensor under the permutation of its various indices. But in fact, it turns out that the derivative of the Riemann tensor also will obey an identity. So the Riemann tensor is a tensor. I could start taking covariant derivatives of it. And it turns out that using Riemann normal coordinates, as we have done before, you can prove that the Riemann tensor obeys one final identity involving its first derivative. This is known as the Bianchi identity. I won't prove this for you because you will prove it for yourselves on the problem set due Tuesday, or maybe the one due the following week. I don't actually remember. But it's proven using exactly the same logic as the identities that I gave you above are proven. You just work everything out in Riemann normal coordinates at a given point, and you start mucking around with the indices. And as we will see in the next few classes, in fact, this Bianchi identity has a very deep physical interpretation, and it is, in fact, what is responsible for the fact that I can construct conservation laws in general relativity. That's one way of viewing it. And moreover, I promised you last time that all of the information in the derivatives of the metric could be packaged into the Riemann tensor. And in order for the counting of those numbers of degrees of freedom to work at orders higher than, so last time I worked to quadratic order in the metric, which involved the Riemann tensor. If I wanted to go, for example, to third order in the metric, I would need to look at derivatives of the Riemann tensor, first derivatives of the Riemann tensor. And you can check, although I won't do so, that this Bianchi identity is a necessary constraint to get all of the degrees of freedom in the third derivatives of the metric to work out. So, in fact, it turns out that all of the various differential equations obeyed by the Riemann tensor are just consequences of the Bianchi identity. But I won't even try and prove that here. Okay. What I'd now like to do is just introduce a few more definitions before we complete our study of differential geometry for the semester. So the Riemann tensor is an awfully complicated beast. It has 4 indices. In your lives as physicists, you've dealt with vectors, you've dealt with matrices, so objects with 1 and 2 indices. You have very rarely dealt with objects with 3 indices, and you probably have never, fortunately or unfortunately, been forced to deal with an object with 4 indices, unless you want to count the volume element in Minkowski space. I suppose that has 4 indices. But aside, you're really not used to dealing with things with 4 indices. And happily, it turns out that a lot of the formulation of general relativity will involve only certain components of the Riemann tensor. So what we will do is, what I would like to do here is define what is known as the Ricci tensor. So the Ricci tensor is denoted R mu nu. So it is has 2 lower indices instead of 4 indices. What is it? It is just the Riemann tensor with 2 indices contracted. So it is a 0, 2 tensor. And what properties does it have? Well, the first property that you can immediately see that is obeyed by this equation, by the Ricci tensor, is that because the Riemann tensor with lower indices is symmetric under the permutation of the first pair of indices and the second pair of indices, the Ricci tensor will be symmetric when I interchange mu and nu. If you stare at this equation, hopefully that will be clear. So the Riemann tensor is a symmetric 0, 2 tensor. And moreover, up to a sign, R mu nu is the unique 0, 2 tensor we can form by contracting indices of the Riemann tensor. So I encourage you to try and check that. Just take the Riemann tensor, contract your two favorite indices together, first and third, second and fourth, whatever, and lower all the remaining indices. And you'll see that because of the various permutation symmetries of the indices of the Riemann tensor, what you'll get is the Ricci tensor, or minus the Ricci tensor. So you should think of the Ricci tensor contains all of the trace information of the Riemann tensor. So if you have a matrix, you're used to defining the trace of that matrix. It's just a scalar by contracting the two indices of that matrix together. If you have a four-index object, you don't get a scalar when you contract two of the indices together. You get a two-tensor. And that tensor, in the case of the Riemann tensor, is known as the Ricci tensor. So the Ricci tensor, so the Riemann tensor is a complete packaging of all of the information about the curvature of space-time. And the Ricci tensor will contain only some of the information about the curvature of space-time. And one can take this one step further. So the Ricci tensor is a symmetric 0, 2 tensor. And I could also take the trace of the Ricci tensor in order to obtain a scalar. Yes, question?
Your second statement that I was based on what happens then if you contract the first and second?
Why don't you tell me what happens?
Well, so this must vanish.
Okay, why does it vanish?
Well, if it doesn't, then you have an anti-symmetric.
Okay, there's a simpler reason why it vanishes. So in the first two indices, the Riemann tensor is anti-symmetric in its first two indices, which means when the first two indices are equal, the Riemann tensor is 0. So the trace of the Riemann tensor in its first two indices is 0. So I should have said that if you trace any two indices of the Riemann tensor, you get r mu nu minus r mu nu or 0. That would have been a more full statement. Yes, good question. Okay. So we also define what is known as the Ricci scalar, which is called R, and that is the trace of the Ricci tensor. And just as the Ricci tensor was the unique 0-2 tensor one could form from the Riemann tensor, the Ricci scalar is the unique scalar that one can form by tracing over indices of the Riemann tensor. So the Ricci scalar is a simpler yet notion of curvature of a spacetime. And roughly speaking, the Ricci scalar is probably the closest to what you have in mind when you intuitively think of a geometry as curved. For example, for a sphere, all of the information in the curvature tensor is packaged into the Ricci scalar, which is just a constant. And so that would be a way of formally saying your intuitive notion that the constant of curvature of a sphere is equal to a constant. The curvature of a sphere is a constant. And I want to remind you that the Riemann tensor packaged all of the information of the curvature of spacetime, so that if the Riemann tensor was equal to 0, then spacetime was just flat. However, the Ricci tensor and scalars only contain information about some of the curvatures of spacetime. So it would be certainly a very interesting question to ask. What sort of geometries have the property that the Ricci tensor vanishes, even though the Riemann tensor might not be 0. Now, geometries where the Ricci tensor vanishes, but the Riemann tensor does not, have a special name. They are known as Einstein spaces. That is not an accident. That is just a bit of foreshadowing of the equations of motion for general relativity that we will begin discussing later this class. Now, before I go on, though, let me do a little bit more foreshadowing. So, the Bianchi identity was an identity involving the first derivative of the Riemann tensor. And one can check, and by one I mean you on your next problem set, that the Bianchi identity also implies an identity for the Ricci tensor. So if you contract one index of your covariant derivative with an index of the Ricci tensor, what do you get? Well, you get something involving derivatives of the Riemann tensor with one index. So the Riemann tensor, the only thing doesn't have any contractions with one index. So it has a contraction with no indices, which is the Ricci scalar. So you would expect that this should be proportional to something involving the derivative of the Ricci scalar, so that it has one lower index. And indeed, you can show, using the Bianchi identity, that if you take the divergence of the Ricci tensor, in the sense that you take the derivative of the Ricci tensor and contract two of the indices together, you get the derivative of the Ricci scalar. So, why is that interesting? Well, we can define the following combination of the Ricci tensor and the Ricci scalar. So let's define something that I will call G mu nu. It's the following linear combination of the Ricci scalar and the Ricci tensor. And I've included a factor of the metric there because, like the Ricci tensor, the metric tensor is also a symmetric two-index object. So this is a linear combination of the metric and the Ricci tensor, which has the following very interesting property. It has the property that if you take the derivative of this tensor G mu nu, and you contract one of the indices of G mu nu with the index of the derivative, you get 0. So G mu nu has a name. It's an interesting name. It's known as the Einstein tensor. And what properties does it have? Well, like the metric and the Ricci tensor, it's a symmetric 0, 2 tensor. And moreover, it is up to a sign the unique tensor that you can build out of the Riemann tensor with the property that grad mu G mu nu is equal to 0. And although I haven't told you this yet, in fact, this second property, which is sometimes known as the conservation of the Einstein tensor, for reasons that will become clear in the not distant future, is a very important property. And as you might guess, it's the property which will ensure that the Einstein tensor is the proper quantity that one should use in order to build the equations of motion of general relativity. So, it's probably worth stepping back for just a minute and recapitulating what we've learned over the last few weeks. So this completes everything that I need to say in this class about differential geometry. We've learned about manifolds, tensors, coordinate systems. We've learned that laws of physics which are coordinate invariant need to be formulated in terms of tensors. We've also understood how to take derivatives of tensors in a covariant manner, and we've constructed the only reasonable notion of curvature in a space-time involving the metric. And what we're going to do now is return to our discussion of physics, and we would like to begin by asking how one can formulate physics in curved space-time, and how it is precisely that the curvature of space-time will lead to a theory of gravity. So that is the subject that I would like to delve into now, and it will lead up to, probably not this class, but certainly next class, a derivation, or at least a quick and dirty derivation, of the Einstein equations, which are the equations of motion of general relativity. So now is probably, if you've been asleep, now is the time to wake up. We're shifting gears, and we're shifting gears in, I think, a much more interesting and much more physics-oriented direction. So you should all be proud of yourselves for having survived the last several weeks' worth of discussions of rather formal mathematics, because now we get to reap the fruits of that study. And so, with the exception of a few digressions into Lie derivatives, killing vectors, and stuff like that, we'll now be doing physics for the rest of this course. So let me pause here and see if there are any questions before I continue. No questions? You know all of differential geometry. Okay. So, the question that I would like to begin asking is the following. So we've spent a considerable amount of time understanding in detail the mathematics of curved spacetime. And so the question that we need to then ask is, how do we formulate physics in curved spacetime? So, up to now, we, in our lives as physicists, have spent a considerable amount of time and effort developing laws of physics which are valid in flat space, and in particular, laws of physics which are valid in special relativity. And the question then is, how do we turn that into a law which will be valid in curved spacetime? So how do we turn laws of physics which we have learned in special relativity, which is to say flat Minkowski space, into laws which will be valid in curved space? So, a priori, there's no unique way of doing this. And you could certainly imagine that if you take your favorite law of physics, electromagnetism, or any sort of law of physics, and you translate it into curved space, there could be, in principle, many different ways of doing so. But there's a principle that we will follow, and it is a principle that must be checked experimentally, and appears to be valid experimentally, but it's a principle rather than a theorem that is true mathematically. And this is known as the principle of minimal coupling, which is how we take a law of physics in special relativity and attempt to formulate it in curved spacetime. So, what is the principle of minimal coupling? So the principle of minimal coupling is based on Einstein's equivalence principle. So Einstein's equivalence principle says that in a neighborhood of any point in space-time, there is an inertial coordinate system, otherwise known as a Riemann normal coordinate system, where the metric is approximately flat, in the sense that the metric at that point is equal to the Minkowski metric, and its first derivative vanishes. So what that means is that at that point, the covariant derivative is indistinguishable from the partial derivative, because they differ from terms involving the Christoffel symbols. So, how do we take a law of physics in flat space and turn it into a law of physics in curved space? So let's start by taking your favorite law of physics, which is valid in special relativity, which is formulated in Minkowski space. And then what we would like to do is interpret it as a law of physics formulated as a tensor equation in curved space written in Riemann normal coordinates, or written in inertial coordinates. So you take your favorite law of physics involving the Minkowski metric, the partial derivatives, and so forth, and you think of that law as a tensor equation, but it's a tensor equation that happens to be written in an inertial coordinate system, a freely falling coordinate system, where the space-time metric is as close to Minkowski as we can get it. And then we take the resulting tensor equation and we declare that that is the law of physics in curved space. Yes?
Or if we want to have a really changing Minkowski space and say, or like a really changing metric,
Mm-hmm.
and see what the law of physics.
Right. So far in your classes, like, let's take electromagnetism as an example. So you know how to formulate electromagnetism in Minkowski space. And the question that we would like to answer then is, how do we formulate the laws of electromagnetism in curved space? And the answer that I would like to give, that I've sort of outlined in these 3 steps, is the following. You take that law of physics of Maxwell's equations, for example, and rather than interpreting them as a law of physics in flat space, Minkowski space, you say that is the law that is valid at a given point in space-time in the Riemann normal coordinates, or the inertial coordinates associated to that point. That will turn the law into a tensor equation, and that'll be a tensor equation that is true in curved space-time. So in order for me to, let me make this a little bit more explicit, because as I've written it, the steps here are logical but a little formal, so it's hard to visualize exactly what I mean. So why don't I say exactly what I mean, and then I think it'll become a little bit more clear. So what does this mean from a practical point of view? So practically, what does this mean? This means that we take our favorite law of physics in flat space which is to say in flat Minkowski space, and then we covariantize. So covariant is generally an adjective. I here have turned it into a verb. So what do I mean by the verb covariantize? Well, a law of physics in Minkowski space will involve things like the Minkowski metric and partial derivatives. And when we want to write that law in curved space, all we do is we take the Minkowski metric and we turn it into the metric in curved space. And we take partial derivatives and we turn them into covariant derivatives. If we have an inverse metric, inverse Minkowski metric, we turn it into the inverse of the curved space metric. And if, for example, you're formulating an action principle which might involve an integral, then we take the flat integral and we turn it into the covariant version of the integral. Oops. Okay, I didn't need to write both a minus sign and an absolute value symbol, although I suppose what I've written is still technically correct. I'll just take the absolute value. So this then is an alternative way of saying the principle of minimal coupling. If you think about it, you'll see that those three steps that I outlined above, where you take a law of physics in Minkowski space and you interpret it as a law of physics in curved space in an inertial coordinate system, is nothing more and nothing less than the statement that you kind of make the obvious replacements. Minkowski metric is a curved metric, and partial derivatives become covariant derivatives. Yes?
If we didn't stick to minimal coupling, what other things could we do to develop?
Well, that's an excellent question. So, let's say, for example, we wanted to try and write down Maxwell's equations. So, Maxwell's equations, one of Maxwell's equations, in the absence of sources, says that d mu of f mu nu is equal to j nu, where f mu nu is the electromagnetic field strength tensor, and j nu is the 4 vector which contains the charge and current densities, as its 0 and 3 components. And so the principle of minimal coupling would say that this becomes the analogous equation involving a covariant derivative. Now, if you think about it, of course it's true that this covariant equation that I have written here will reduce down to this equation that I have written in flat space if you just evaluate it in R3, 1. But there are many other sorts of equations that I could write down that will also reduce down to this equation in flat space. So, for example, a non-minimally coupled version of this equation would be the statement that the derivative of the electromagnetic field strength is equal to the charge, the current 4 vector, plus terms, that happen to be 0 when you're in Minkowski space. 1 plus r, where r is the Riemann curvature. The Ricci scalar. Okay? The Ricci scalar times j nu is that's still a vector. It's a scalar times a vector. It's still a 1 form. Scalar times a 1 form. So this is certainly a law of physics that you could write down, which would reduce to the correct law in flat space-time. And it's certainly consistent with all that we've said about the tensorial nature of the laws of physics. Physics would be extremely strange, just a second, in a universe where this law was true. In fact, it would muck up all sorts of physical principles like gauge invariance and stuff like that. But in principle, the principle of minimal coupling is not something that we can derive from first principles. It's just something that we have to test, and we have to check observationally or experimentally to the extent that we can. Yes, question?
I guess writing that, the Ricci scalar doesn't vanish.
The Ricci scalar does not vanish in Riemann normal coordinates, but it does vanish in flat space, right? So in general, what do we need? What sort of physics do we need? What sort of equations should we be writing down? Well, in general, we only need to write down equations that we know. If we know all of physics in flat space, then we want to write down a law of physics in curved space-time. All we know is that that law of physics has to reduce to the correct equation in flat space. So here I've written an example of a version of Maxwell's equation which will reduce to the correct Maxwell's equation in flat space. But in principle, there could be corrections to Maxwell's equation that involve the curvature of spacetime in some way that's more complicated than the principle of minimal coupling would allow.
So I guess my last question is, if your laws of physics reduce to something that looks like something flat spacetime in normal coordinates, does that apply minimal coupling?
Sorry, say that again?
If the laws of physics reduce to something that look like the laws of physics in flat space-time.
Yes. Yes, that's a way of saying it. That's another way of saying the principle of minimal coupling. The principle of minimal coupling, another way of saying it is that when you write your laws of physics in Riemann normal coordinates, they are the laws of physics in flat space. That's another way of saying it. And that's just a guess. Or a principle, if you want to give a fancier name for it. And it appears to be true in all of the settings where it has been tested. But like many things in general relativity, the tests aren't all that great. So it's certainly possible that there are complicated couplings between electromagnetism and the curvature of spacetime that go beyond the principle of minimal coupling that simply haven't been observed yet. Possible, unlikely, but possible. Actually, in that case, I think the tests are probably pretty good. But as we will see in general relativity, the gold standard for experimental tests in physics are the tests of quantum mechanics, for example, or the tests of special relativity, which are phenomenally accurate. But the experimental tests of general relativity are not as good as those of quantum mechanics or special relativity. And so it's important to remember that these are some of the things that we are discussing are things which still one needs to be careful to check experimentally. Question?
Is this an analogy to F theories, for example?
For example, yes. So there's, as I'll mention a little bit when we discuss the action of general relativity, the equations of motion of general relativity that I will write down are the correct ones according to a given set of principles that I will describe for you. But there are other equations that one could write down, which we will discuss when the time comes. Yes. There was a question? Yes.
How does this compare to the problem of quantization when more than one system has the same classical limit?
I would say it's morally of the same character as the problem of quantization.
Principle that people use in quantum mechanics?
Yes. In some sense, in general relativity, we say there is a principle, at least, which allows us to write down a law of physics in curved spacetime given a law of physics in flat spacetime. In quantum mechanics, you would ask, given a classical phase space and Hamiltonian, can you write down a quantum mechanical Hilbert space and the corresponding Hamiltonian? There is not even a principle. You need to have certain extra structure on the classical system in order. There's what's known as geometric quantization, which is a principle that's valid in certain circumstances. But I would say that the quantum mechanics, we're in even more trouble in quantum mechanics than we are in classical physics. In general relativity, sorry. Yes?
Yeah, so this is according to the second point, but according to the third point, there will also be corrections due to the higher radius of symmetry.
Absolutely. Yeah. So, for example, if you look at Maxwell's equations in curved space, then in Riemann normal coordinates, if you expand it only to order x hat, everything would look exactly like it does in flat space. But if you're in a curved space-time, there'll be corrections involving the second derivatives of the metric, right? And so Maxwell's equations in curved space are not the same as Maxwell's equations in flat space. They're Maxwell's equations in curved space. And they have to be analyzed, and their physical implications will be different from Maxwell's equations in flat space. And in some cases, there are observational consequences of those differences. We live in a curved space. The universe is expanding. That means that space-time is curved. That means that the properties of Maxwell's equations, such as the properties of the propagation of light, are different in curved space than they are in flat space. That's why, for example, when you look at galaxies, they are redshifted. I mean, I'm getting far ahead of ourselves, but there are certainly very, very powerful, well-tested experimental verifications of this. Okay, let me give one. Oh, Jesus Christ. Okay, let me not give one more example. Let's stop here, and I'll see you all tomorrow at 4 p.m.